Hello, Chem 2, and welcome to the seventh, that's right, I said seventh and final video for Chapter 3, where we will discuss the combustion analysis. In the last video, we looked at three application problems, three ways to use the stoichiometry we've used from Chapter 3. Definitely, the last video was significantly more complicated than those first videos where we were going from moles to mass or moles to particles. The application aspect is pretty astounding. But this application happens to be very, very common and is very, very, I don't want to say simple, but a very direct type of analysis. It can be expanded outside of the typical combustion analysis, but I just want to use this as a springboard, a chance to see how you can analyze a sample in a slightly different way. So I have two example problems, both of which are very similar. One's a little more complicated than the other. And our goal is to find out if we burn a substance that we know at least a little bit about the substance, a little bit about its composition. If we burn that substance and we allow it to go through a complete combustion analysis, we should be able to figure out what the empirical formula is and ultimately the molecular formula. Neither of my examples actually go to completely to molecular formula included, but we saw that in video number 4 or 5. I don't know. Anyway, let's get started. So a combustion analysis is a reaction where you take a sample that contains carbon and hydrogen, and this one only contains carbon and hydrogen. Next one's going to get a little bit of extra stuff in there. So let's see if I can get my pen to work. Just go down here. There we go. So a combustion analysis has carbon of some amount. I don't know what it is. Hydrogen with some amount. And a combustion reaction always reacts with oxygen and makes carbon dioxide and water. Now, the pivotal piece of doing a combustion analysis is the realization that all of the carbon that is in the carbon dioxide came from your compound. And secondarily, all of the hydrogen that was in your water came from your original sample. So if we are able to figure out how much carbon is in the carbon dioxide and how much hydrogen is in the water, we should be able to figure out the ratio of the number of carbon atoms and the number of hydrogen atoms. That's the goal here. So let's look at this. So we have a 1.5 gram sample. It goes through analysis, and we get 4.4 grams of carbon dioxide, and we get 2.7 grams of water. Let's give it a shot. Okay, so I've already said that the basic reaction is carbon, hydrogen compound only, plus oxygen to give you carbon dioxide and water. So what I'm going to do first is try to figure out how many moles of carbon there are in all the carbon dioxide I have. So if I have 4.40 grams of carbon dioxide, and I know the molar mass of carbon dioxide is 44.0095 grams per mole, and I know that in carbon dioxide there's 1 mole or 1 atom of carbon for every mole of carbon dioxide. That tells me if I do this math right, I get 0.100 moles of carbon. Let me do the same thing with hydrogen. So if I start with the 2.70 grams of hydrogen, and I divide it by the molar mass of water, which is 18.0153. And here's the tricky part. I can see, it's not really that tricky, that there are 2 moles of hydrogen for every 1 mole of water because it's H2O. And if I do that math, I get 0.300 moles of hydrogen. So if I divide by the smallest number, which is 0.1, I see that I have, for every 1 carbon, I have 3 hydrogens. That's my empirical formula. Done. Okay, so the basic concept is that you're going to figure out the number of atoms of carbon and atoms of hydrogen from the products. Let's see if we can make this a little more complicated. Okay, so now I have a different compound, and here's the trick, twisty part. This vanillin compound is found in vanilla, hence the name vanillin, contains three elements. It contains carbon, hydrogen, and oxygen. It's still going to combust with oxygen, and it's going to make carbon dioxide and water. And that's cool. But notice we're going to think the same way. All the carbons that are in vanillin are in carbon dioxide. All the hydrogens that were in the water came from the vanillin. But the oxygens, did these oxygens that are over here come from the oxygen gas that we reacted with, or did it come from the vanillin? So we have to do something a little special to find out how much oxygen there is. So let's see. We're going to start by doing what we did on the previous, and that's worry about the carbon dioxide and the water. So we're going to start by saying I've got out my 2.43 grams of carbon dioxide at 44.0095 grams of carbon dioxide per mole of carbon dioxide. And still, for every 1 mole of carbon, I had 1 mole carbon dioxide. And I get a number. Let's see what that is. I did this already. I get 0.0552 moles of carbon. Now I'm going to do the same thing again for my water. And I made a mistake when I did this originally, so I'm going to be careful here. Because 0.50 grams of water, and it's 18.0153 grams per mole for water. And there's 2 moles of hydrogen for every 1 mole of water. So when I did this, I got 0.0556 moles of hydrogen. Okay. Now, what about that oxygen? That's where things get a little challenging. I know that my original sample was 1.05 grams. And that was from the carbon, the hydrogen, and the oxygen. So if I can figure out how many grams of carbon I have, and I can figure out how many grams of hydrogen I have, I should be able to figure out how many grams of oxygen were left over. So I'm going to do one more step here. I'm going to multiply each of these by their molar mass. And I get that the mass of carbon from the top equation is 0.663. And I get the mass of hydrogen from the second equation to be 0.0559. I'm just kind of throwing sig figs way out the window here. So I need to find the mass of oxygen. So I take 1.05 minus 0.663 minus 0.0559. And if I do that and worry about sig figs now, finally, I get that I had 0.33 moles of oxygen. Cross that, grams of oxygen. So now I got to figure out how many moles that is. So if I have 0.33 grams of oxygen at 15.9994 grams per mole, I get 0.0206 moles oxygen. So I know the moles of carbon, I know the moles of hydrogen, I know the moles of oxygen. So what I'm going to do here is I'm going to compare those. So if I have, for carbon, I have 0.0552, and for hydrogen, I have 0.0555, and for oxygen, I have 0.0206. I need to divide each one of those by the smallest number, which is 0.0206. And I get a ratio of, and this is kind of fun because I didn't see this coming, but I'm glad I did, of 2.67 to 2.67. I think it's trying to be 6.8 to 1. Now, those aren't whole numbers. But you remember when we did empirical formula, I said, be on the lookout for numbers like 0.66, 0.67. So I need to multiply each one of these numbers by a number that will make it whole. If I multiply each of these by 3, I get an 8 to 8 to 3 ratio. And yes, vanillin is C8H8O3. That's the empirical formula and the molecular formula for vanillin. So that's the last video for chapter 3. In class, we will continue to do some practice problems to get you more and more ready for these. What we're going to do now is, after this, we're going to have 1 day of practice overall, and then we are going to be having an assessment on just chapter 3 alone. So until next time, until I get a chance to put together another video, this has been one very, very long weekend of videos. Stay safe, stay healthy, practice that social distancing, and toodles.